Good morning. So yesterday when we discovered the importance of describing motion in terms of position and time. We can do this with both graphical representations, which we have looked at, and mathematical models, which we are going to look at from today. And we are going to see what information we can gather in using these two different representations. Okay. So before we get started, we just need to talk about some different terminology that we can use to describe the motion of our object. Okay. So as an example, let's say we have an object that starts here. It moves 10 meters up, 10 meters to the right, 20 meters down, 20 meters to the left, and then 10 meters up. Okay. What we want to do is we want to just use this motion to describe a couple different things. The first thing we're going to talk about is distance. Okay, so distance is going to talk about how much total ground. Okay, so how much ground in total did our object cover over our time of motion? Okay. So if we look at our example here, if we want to find our distance, we're going to add up the individual distances traveled by the object in total. So first we went 10 meters up, then we went 10 meters to the right, then we went 20 meters down, 20 meters to the left, and 10 meters up. So all in all, our object traveled a total distance of 70 meters. Okay, so distance, we're just saying how much total ground was covered by an object. Notice how when we were finding our distances, we did not include direction. And because of that, we're going to define distance as a scalar. Okay? And when we talk about scalars, a scalar is going to be a quantity that is just a number. Okay, it just has a value, but it does not include direction. So only magnitude, so only the value of a variable and no direction. So we're not going to include any positives or negatives when we are looking at this. We're going to treat everything as one sign. That is going to be different than displacement. When we talk about displacement, we are going to find the difference between our starting and ending position. And in order to do that, we're just going to take our final position minus our initial position. Remember, we're going to use the variable x to represent position here. So displacement, our change in position, is going to equal our final position minus our initial. So if we look at our example here, we just want to see how far our object ended compared to where we started. Vertically, it's at the same position. It's only going to be 10 meters to the left. Okay, so our displacement in this example would be 10 meters west or 10 meters to the left, because we end 10 meters left of where we started. Because we take into account direction with displacement, you're going to call this a vector quantity. Okay, so unlike scalars, vectors, we're going to have magnitude, so a value, and direction. So with displacement and vectors, we can include negative signs here. All right, so let's look at an example. Let's say we have a turtle with a jetpack and its motion is described in this position versus time graph. Okay. We want to find the total distance that the turtle covers. So what we're going to want to do is we're going to want to look at each segment of our graph and see how far or how many meters our turtle traveled over that period of time. So if we look at 0 to 5 seconds, we started at a position of 0 and we ended at a position of 30. So from 0 to 5 seconds, our turtle traveled 30 meters. Then if we look at 5 to 10, here we can see our position is not changing. So our turtle stopped and did not cover any distance there. However, then when we go from 10 to 20 seconds, here our turtle started at a position of 30 and ended at a position of 10. Okay? So here our turtle went backwards 20 meters. Okay? 20 to 25 seconds, just like what we saw at 5 to 10, our turtle stopped. Our position is not changing. And then from 25 to 30, they were starting at a position of 10 and ending at a position of 20. So there, our turtle traveled 10 meters. So when we want to find our total distance our turtle covers, okay? Remember, this is going to be a scalar, so we're not going to include direction. We're just looking how much ground in total did our turtle cover. So what we're going to do is we're just going to add up the distance the turtle traveled at each one of these individual segments. So from 0 to 5 seconds, our turtle traveled 0 meters. 5 to 10, didn't travel any. And to 20, it went backwards 20 meters. But because we're looking at distance, we're just going to treat this as a positive 20. Again, distance does not include direction. We're just looking at how much ground in total did we cover. 0 meters from 20 to 25, and then our final 10 meters from 25 to 30. And when we add these all up, we should find that our turtle covered a total distance of 60 meters. Okay, so again, total distance is the total ground that our object is traveling. For displacement, however, here we're just going to compare our final position of the turtle and our initial position. So if we look at our turtle, he ended at a position of 20. And he started at the origin, or at a position of 0. So because our ending position is 20 meters ahead of where we started, our total displacement here is going to be 20 meters, okay? And since this is displacement, it's going to be a vector. So we want to include direction here. So we're going to say this is a positive 20. He traveled 20 meters in the positive direction. So for these guys, even though he traveled a total distance of 60 meters, he only ends 20 meters in front of where he started. So our displacement for the turtle is only going to be 20. Use the words distance and displacement to describe the turtle's change in position. How far is it moving? Then how can we describe how fast the turtle is traveling at? So we had talked about in our Buggy Lab discussions that we can tell how fast our object is moving by looking at the slope. So in order to find how quickly the turtle is moving at each time frame, we're going to want to find the graph slope at each of one of those individual time frames. Okay, so go ahead and take a second and find your slopes for each of these individual time frames based off of this graph. All right, so as a reminder, when we find our slope, what we want to do is pick 2 points on our graph or 2 points on our line and find the difference in our y values and divide that by the difference in our x values. So we can do that for each one of these individual segments on our graph, okay? So if we find our slope from 0 to 5 seconds, we should find there that our slope is 6 meters per second. 5 to 10, and from 20 to 25, we have that horizontal line. So that tells us our slope is 0 meters per second. And this makes sense because we said our turtle stopped at those time frames. So if our turtle is stopped, it's going to be traveling at a rate of 0 meters per second. When we look at 10 to 20, here we can see our turtle is traveling backwards. So we can see that our slope here is going to be negative. So from 10 to 20 seconds, we have a slope of negative 2 meters per second. And then from 25 to 30, here we're moving forward. And our slope is here positive 2 meters per second. Okay. So when we look at our graph then, or data, at which interval is our turtle going to be moving the fastest? So in order to figure that out, we want to find where our slope is the greatest. So that's going to be from 0 to 5 seconds. because the slope is the steepest, so we are traveling the most meters for every 1 second. Our slope is kind of give us information on two different things: our speed and our velocity. Okay, and with our speed, this guy is going to be linked to distance. Speed, like distance, is going to be a scalar quantity. Okay, so that means it's going to have magnitude, or it's going to have a value with no direction. Okay, so we're going to treat everything as positive here. So your speeds will always be positive. And in order to calculate our average speed, what we're going to do is we are going to take the distance that our object traveled divided by the time that it took to travel that distance. Okay? So an example of this could have been or 6 meters per second or 35, let's say, miles per hour. Okay? This is going to be different than velocity, and that velocity is going to be linked to displacement, and then therefore going to be a vector quantity. So that means we have magnitude. So we have a value and direction. We have both things here, telling you how fast our object is moving and in what direction it is traveling. So these guys can be positive or negative. Okay. When we want to calculate our average velocity, okay, it's going to be similar to our speed equation, except here we are going to use our displacement. Okay, because displacement is also our vector divided by time. So an example of our velocity could have been our -2 meters per second, or if we had said 35 miles per hour east. Okay, we're adding direction to that speed. Okay, so then for number 4, we want to find the turtle's average speed between 0 and 20 seconds. So when we are looking at speed, we're going to do distance divided by time. So I know my time frame here between 0 and 20 seconds is going to be 20 seconds. I need to go up and see what distance my object traveled between 10 and 20. So I scroll up to my graph, and I'm just going to look at 10 and 20 seconds. So from 0 to 5 seconds, we said we traveled 30 meters. 5 to 10, we didn't travel any at all. And then 10 to 20, we traveled 20 meters. Okay? Since we're looking at speed, which is a scalar, we're not going to pay attention to the direction that our object is traveling. So we're just going to take our 30 meters plus 0 meters plus 20. Okay, so we're just adding up the total distance that our object covered between 0 and 20 seconds. And we should find our average speed here is 0.5 meters per second. That is going to be different than our velocity, because velocity, we're going to use our displacement over time. Okay, remember, displacement, we take into account direction. So we'll still have our 30 meters that we traveled forward, the 0 meters where we stood still. But here we're going to subtract the 20 meters that we traveled backwards. Okay, so displacement and velocity, we're taking into account the direction. And then we're again over a time interval of 20 seconds. So when we plug this in our calculator, we should find that our average velocity is going to be positive 0.5 meters per second. Okay, so on average, and from getting from our, let's see, initial position of 0 to a position of 10 at 20 seconds, our object traveled at a rate of 0.5 meters per second. Okay. So then for number 6, what we can do is we can write an equation to describe the motion of our object at different intervals. So we know for our equation, we like to use the general equation, y equals mx plus b. But remember, we don't like to just say y and x. We like to say what variables these letters represent. So on our y-axis, we have position, our slope from 0 to 6. Remember, that's the same thing as our speed or velocity. So when we come up from 0 to 5, we saw that our speed there, or that our slope, was 6 meters per second. So we'll plug that into our equation. We want to multiply that by our x variable, which on our x-axis we have time. We multiply that by time, plus our y-intercept, and we can see at time 0, we start at a position of 0 meters. Okay? So we can describe the motion of our turtle from 0 to 5 seconds with the equation position is equal to 6 meters per second times the time plus 0. So if we wanted to find our object's position at 1.5 seconds, we could then plug in that 1.5 into this equation for our time and solve for what our position would be at that time interval. So let's say we have this position time graph with object A and object B. If we want to see which object is moving faster, we are going to want to look at our slopes and see who has the steeper slope to tell us who's moving the fastest. If we look at A and B, we are going to see that B has a steeper slope, so it is moving faster. Okay. It's okay that that slope is negative because that just tells us that B is moving in the negative direction. Okay. It's still moving at a faster rate. It's just moving in the negative direction. Whereas A, here we have a positive slope, so it's moving in the positive direction. Okay, so the signs of our slope will tell us what direction we're moving, whereas the value or magnitude of our slope will tell you how fast our object is moving. Okay. All right, so then when we look at number 2, here we have an object's position time graph over a time interval. All right, so here, when we want to see what direction our object is moving, we are going to look at the sign of our slope. And we are going to see here that we have a positive slope. So we're going to be moving in the positive direction or forward. Okay. When we want to find the object's speed, in this case, we're going to do distance divided by time. So if we look at this object, we can see that it starts at a position of 5 and ends at a position of 25. That means our object traveled a total of 20 meters. And since we're looking over a time interval of 4 seconds, we're going to divide that by 4. So find that our speed here is 5 meters per second. Okay. Another way we could find that is just by finding the slope of this line. In this case, when we're finding velocity, remember, velocity, we do displacement over time. So for displacement, we compare our final position, the 25, to our initial position of 5, and we want to find that difference. Okay, that'll tell us our displacement. How far did we end compared to where we started? And then again, that occurred over an interval of 4 seconds, so we divide that by 4. And in this case, we're again going to find that our velocity is 5 meters per second, but we're going to say that that's a positive 5 because velocity we want to include sign. So notice that our speed and our velocity here give us the same value, okay? That's totally fine because our object is only traveling in the positive direction here. Since we're not traveling in the negative direction at all, our speed and velocity are going to end up being the same because we don't have any negative signs to take into account when calculating our velocity. So it's a-okay if we get the same thing for the speed and our velocity if we're only traveling in that positive direction. All right, so then for our mathematical model, we know we want to use the equation y equals mx plus b. But instead of just saying y, we're going to say what is on our y-axis. So position is equal to our slope, which is going to be our velocity of 5 meters per second, times our x variable of time, plus our y-intercept, which we can see here is 5 meters. Remember that y-intercept, that 5 meters, tells you your starting position of your object. Okay, so the y-intercept tells you where your object is starting off. Okay, so then 3, this one's a little different because we have multiple segments, and we're going to want to describe the object's motion at each individual time interval. So we're going to kind of break this up into 3 chunks. The first one being 0 to 1, the second one being 1 to 3, and then our third and final being 3 to 5. Okay, so if we look at 0 to 1 seconds, we can see that we have a negative slope. So that tells us our object is moving in the negative direction. Okay. If we want to find our object's velocity, what we are going to do is do displacement over time or find our slope. So we can pick 2 points on our line, say 0, 4, and 1, 2, find the difference of our y's, and divide that by the difference in our x's. And we should find that our slope here is going to be negative 2 meters per second. So our object is traveling with a velocity of negative 2 meters per second. For every 1 second, it's traveling backwards 2 meters. Okay. So then if we look at 1 to 3 seconds, here we have a horizontal line. So our object is going to be motionless. Our position is not changing. Okay. And since our position is not changing, we have that horizontal line. Our velocity in this case is going to be 0 meters per second. Okay, because we know when we have a horizontal line, our slope is going to be 0. So then we can look at our last segment of 3 to 5 seconds. Here we have a positive slope, so we know our object is going to move the positive direction. Okay. And we want to find the rate at which its position is changing. So we're going to find its velocity or our slope. And remember, when we find our slope, we're going to pick 2 points and find the difference in our y's and divide that by the difference in our x's. So we could do the points 3, 2 and 5, 3. So then we can do our difference of our y's, 3 minus 2, divided by the difference in our x's, 5 minus 3. And we should find that our slope here, our velocity, is going to be 0.5 meters per second. Okay, and we're going to show that it's positive because velocity includes direction. Okay. If we wanted to think of that as displacement over time, that works perfectly well too. Because if we're comparing our initial and our final position from 3 to 5 seconds, we can see that we end at a position of 3 when we started at a position of 2. So we would have a displacement of 1, and then we divide that by our time interval of 2 seconds, and we end up getting the same thing. So whether you want to think of it as finding your slope or by doing displacement over time, either one works when you're looking at those individual line segments. Okay. So for tomorrow, you guys will finish the rest of this packet. So just getting more practice finding our distance, our displacement, our speeds, and our velocities by using a position versus time graph. Please let us know if you have any questions.